So with that, we will get started. Today's keynote speaker is Joshua Ross. Josh Ross. He's Chief Engineer for Satellite Servicing with Northrop Grumman.
Excellent. Thank you for having me. This is my first time at the Flight Software Workshop. I've been super impressed by all the presentations so far, and we're at about the halfway point, so I'm looking forward to the rest of today and tomorrow. As mentioned, my name is Joshua Ross. I'm the Chief Engineer for Satellite Servicing at Northrop Grumman. I'm here to talk about how the space economy is evolving due to new and emerging capabilities for on-orbit servicing. I'm going to talk a little bit about what we've done so far, what we already accomplished, what we see as the next big steps, where we're going, and what we're going to need from flight software to really make those future capabilities into a reality. So I noticed, I came up with the title of my presentation before I completely filled out all of the content. It's not really the future of flight software, but the future of what we need from flight software to make the future actually into a reality. So first, a little bit of background on me. I have an aerospace background, not flight software. So please bear with me a little bit on this. I got my undergrad from in aeronautical and astronautical engineering from the University of Washington. Go Huskies, if there's any other Huskies in the audience. I then became a rambling wreck from Georgia Tech, got my master's in aerospace engineering. And then I joined Northrop Grumman and have spent the majority of my career working on advanced space missions. Now, I've done a variety of things. I've worked a number of different roles, worn a lot of different hats, often multiple hats at once. I've done systems engineering, mission analysis, integration tests, mission operations, done a little bit of everything. So I started my career in Cygnus. Now, this isn't the Cygnus that you may hear as you walk around SwRI. This was the NASA Commercial Resupply Services, or CRS vehicle. It's a vehicle that takes supplies and payloads up to the International Space Station. Now, when I supported the first 10 of these missions, and when NASA first started this program, there was a little bit of skepticism in the space industry about relying on a commercial partner for such a critical function in the NASA mission, keeping the space station supplied. But today we sent 20 Cygnus missions up to the space station, delivered over 60 metric tons of cargo. And NASA's really come to rely on Cygnus and the other CRS vehicles to keep the ISS functioning. We really took, what some people at the time thought was too risky or maybe impractical, and turned it into the new standard. So along the bottom, you have a couple of pictures. I sprinkled in some real photos of spacecraft throughout the presentation. The first is one of our vehicles after it was captured by the Canada arm. They do an inspection for debris and damage before they berth it up to the space station. The second is astronaut Karen Nyberg, as she is getting ready to unload our very first vehicle, the Orb D1. And then over on the right are the mission patches for the 10 Cygnus missions that I supported. So from there, I transitioned over to the mission extension vehicle. Some people from SwRI supported this, may be familiar with it. So we call it MUV for short. So the concept of MUV was really born from to address an unfortunate reality of space missions that, especially in the GEO belt. So those that may not be as familiar, the GEO belt is where we have a lot of high-value communication satellites. That's where they operate. It's very convenient because they don't move relative to the ground. Well, when one of those satellites runs out of propellant, they're required to deorbit themselves up to what's known as the GEO graveyard. Now, besides running out of propellant, these vehicles may be perfectly healthy otherwise. They may still be able to provide value to the operators. This is kind of like throwing away a car because it runs out of gas. It's an unfortunate way to do business. So this is where MUV comes in. MUV docks with these vehicles either in GEO or in the graveyard, and then uses its own propellant to do maneuvers, station keeping, attitude control, so that the client can continue to operate well beyond its propellant life. So going back a little bit, when I joined Cygnus, the design was already pretty mature. It was past CDR. All I had to do was help the program get across the finish line and then do it 9 more times. When I joined MEV, it was really just an initial concept. We were very, very early in the program. We knew what we wanted to do, but we didn't have a design. We didn't know the ConOps. And I had the privilege of being on the team that took that initial concept, matured it, developed it, and actually turned it into two fully operational vehicles. The first was MEV-1, which in 2020 made history docking to the Intelsat IS-901 vehicle. Now, this was historic for a couple of reasons. First, this was the first time two commercial satellites had ever docked in space. And this was also the first time that any vehicle, commercial or otherwise, had docked to another one that was unprepared. It had no interfaces. It was not designed to be docked with. So MEV-2 then followed this up, not only repeating the success of MEV-1, but actually upping the ante a little bit. It docked to the Intelsat IS-1002 while it was actively broadcasting to over 18 million users, and not a single drop of service was noted. So just like Cygnus, we took something that a lot of people thought was too risky to dock in the geo belt. This is where, as I mentioned, a lot of high-value satellites are. If anything went wrong, we could cause problems for a lot of providers. We took that and we actually made it operational, and it's out there working right now. Between MEV-1 and 2, we've provided over 7 years of life extension, and they're both going strong today. So again, a couple images on the bottom. The first one is MEV-1 prior to launch, fully assembled, ready to go. You can see some people in there for scale. The next images are actually from the MEV vehicles while they were in orbit in GEO. The first is as we were approaching the IS-901 vehicle. That's MEV-1. The next one is also MEV-1 in the process of docking to IS-901. You can see our probe getting in, grabbing the client vehicle. And the last one is MEV-2 as it approaches its client. Now, one thing I'll just point out, I find it interesting at least. The MEV-1 images are visible spectrum. MEV-2 is infrared. Now, both vehicles were outfitted with the same cameras. I just like to put the two up there to kind of show the difference in capabilities that we have and how similar actually the visible and the IR spectrum turned out to be. So here's actually a video comprised of images from the MEV-2 mission. This is the IS-1002 vehicle that you see up there. So in this video, you'll see MEV-2 circumnavigate the client, getting closer and closer, navigating a set of waypoints. And as it gets closer in, it's going to actually change to a different camera, and you're going to focus on the nozzle on the back end of the client. So we use this nozzle as kind of a capture phone. So just to kind of foot stomp this, we approached to within a meter of another vehicle in the geosynchronous orbit, flying at 3,000 meters per second, 36,000 kilometers above the Earth. And we inserted our probe into an aperture roughly the size of a quarter. To say it was exciting to be in the control center when they announced that docking was complete is to understand. This was an amazing achievement that I'm going to remember for the rest of my life, being in that control center. And the success, it came after years of hard work. As I mentioned, a lot of people from SwRI supported this. They know this was not an easy mission. It came from, literally thousands of mission simulations, dozens of rehearsals. Flight software played a huge role in their various capacities of fault management, image processing, GNC, just to name a few. So besides the first-time achievements and the cool imagery that we got from these MEV missions, they actually mark kind of a paradigm shift in space missions as a whole. One day we might look back and see the evolution of space missions, that there was a very clear marker. There was a time before satellite servicing and a time after. And these are the missions that really mark that transition. So building on the success of MEV, we're now looking at working on our next generation systems. These are going to provide our clients with more ability to live longer, provide more capability, and respond to needs after launch. I'm going to get into all that a lot as we go through. This is going to provide our customers with competitive advantage and operational sustainability that they just don't have with today's satellite industry. So our goal is to establish a satellite servicing ecosystem of a range of different vehicles that can do different capabilities for different services on orbit. And this is really aimed at making space missions more sustainable, more flexible, and more resilient. So we're currently working on 2 new vehicles. The first is the mission robotic vehicle. You see that here on the left. We call that the MRV. The next is the mission extension pods, or the MEPs. That's the smaller one on the end of the arm. So MRV uses robotic arms that are provided by DARPA to capture the MEP and install it onto clients that are running low on propellant. It then kind of acts as a life extension jetpack for these clients, similar to how MEV worked, but it's smaller and more affordable. The MRV can also do other things with its arms. It's definitely not designed just for MEPs. On the far side, you can see a couple clips of other capabilities that we have. We can do up-close detailed inspections for clients that are experiencing some anomalous behaviors. They need some help really investigating to see what it is. We can do the detailed inspections. We can do some repairs. So here you see us deploying a solar array that didn't fully deploy on its own. We can also do things like moving blankets that came dislodged during launch, just to name a couple. And we can also use our robotic arms to grab onto the client and reposition it, either move it to the geograveyard, from the geograveyard, or move it around the belt so it can actually service a different geographical region. Now, what we're doing with these vehicles, it may seem kind of sci-fi. I mean, we're using robots in space to combine multiple vehicles together, create something that's bigger with more capabilities. It kind of brings to mind Megazord from Power Rangers, combining a bunch of things together. But as cool as this is, we think what comes next is actually going to be even cooler. So MEV, MRV, and MEP, they're designed to service unprepared customers. These are customers that were never designed to be serviced. They have no interfaces for servicing. When they launched, satellite servicing wasn't even an option to be considered. But we think as satellite servicing becomes more established in the industry, more commonplace, future missions may actually design in interfaces into their mission design that will allow for more complex, more sophisticated services. These services would allow us to really rethink how we do and plan space missions. They would allow us to rethink how we treat consumables and how we respond to needs after launch. As we know, things change over time, and this being able to address that over time will be a huge benefit to the space mission. So let's take refueling, for example, to start with. So to bring it to something that we can all relate to, imagine you go to the grocery store, you pick a bunch of stuff for dinner, you get home and you realize you forgot one key ingredient. I mean, it happens to me all the time. I forget my head if it wasn't attached sometimes. So you just hop in your car, you run back to the grocery store, you pick up what you need, you don't think twice about it. Or maybe it's a beautiful day outside. I haven't seen any of those here in San Antonio yet, but occasionally the sun does come out. You have a convertible, you want to go for a little joy ride, drop top down, feel the wind in your hair. I mean, not really an option for me, but for those of you that have it, enjoy it. You don't consider how that extra gas that you use is going to affect you in 10 years. If you run out of gas, you go to the gas station, you fill back up, and you go on your way. You don't think about it. But this is a luxury that space missions don't have. What they launch with is what they have for the rest of their life. They have to account for every drop of propellant that they use, because as soon as that runs out, there's no gas station on orbit. There's no way to refill, at least not yet. So we've already demonstrated on a couple of missions the ability to flow propellant from one vehicle to another. And with the right interfaces, this really enables on-orbit refueling. I've heard a couple of other people mention this. I am really excited to see that in the industry, we're all recognizing the importance of this as a next step. Being able to refill means you don't have to carry everything with you from launch to the end of your mission. There are some missions today that launch with hundreds of kilograms of propellant, and they just have to lug that around for every maneuver, for everything that they do for the rest of their mission. They have to carry all of that propellant with them. Being able to refill means you can carry less at any given time, making your vehicle lighter, making it more efficient with its maneuvers. It allows you to maneuver more frequently, moving around in space more dynamically with more agility. Now, we see this as such an essential capability that we've invested significantly in developing our interface for on-orbit refueling. We call it the passive refueling module and the active refueling module. The two of them meet together. The Space Force actually recently recognized our passive refueling module, the PRM, as their first and so far only preferred standard interface for on-orbit refueling. Now the PRM, it kind of acts like the gas inlet for your car. It's a little thing that sits on the side of the vehicle. You don't think about it too often. When you run low on propellant, you just hook up to it, flow some propellant, and you go on your way. Because it's in space, it's a little bit more sophisticated than what's on your car, but the idea is still there. It's something that we're all very familiar with, and we can all imagine how it would function. You're going to see this theme keep coming up, where we want to take things that work really well in our everyday lives and make them available to space missions and satellites in orbit. So along these lines, another thing that works really well in our everyday lives is standard interfaces for power and data, things like the USB. So when you buy a new smartphone, you're not limited to what comes with it in the box. With a USB connection and the right software, the right app, your options for add-on peripherals is virtually unlimited in today's market. So we want to take the same kind of concept and bring it to space for on-orbit augmentation. These kinds of interfaces would allow us to add entirely new capabilities after launch. Space missions are designed to last years, sometimes 2 years, 5, 10, 20 years. If you think about the technology that we had available 10 years ago and how much has advanced since then, where we are today, unfortunately, space missions can't leverage that advancement. When they launch, their technology is pretty much frozen. It's actually well before their launch because they have to design it in to their vehicle. So when they launch, technology advancement stops. But with the ability to add on new things after launch means that that's no longer the case. We could then respond to new opportunities, new market trends, or maybe new threats as they arise over the next several years. You would no longer be bound to the paradigm of the technology that was available at launch is what you have available for the rest of your mission. These kinds of interfaces would also allow entirely new classes of mission. So I'm sure a lot of people here are familiar with as a service as a business model. They have software as a service, cloud as a service, ground as a service. With plug-and-play type of interface on orbit, we could do something called bus as a service, where you have someone that provides a vehicle that does all of the essential capabilities, the attitude control, the power, the comms. And what you would then have to do is just design your payload to have this common interface, and you just plug it in. You don't need to know anything else about the spacecraft. You don't need to know how to build it, how to fly it, how to test it. Essentially, you would open up the space to allow, we saw some talks yesterday and earlier in the week about wanting to really advance TRL and get their new thing to a point where they could sell it on orbit. Having this access where you don't need to build a whole spacecraft, you just need the payload, means that we can advance our TRL much faster. It would also make access to students at the university level or even down at the high school level. It would give them more opportunity to actively participate in space because, again, they don't need to know everything. They just need to know that their one little thing works with the interface that it's designed for. And you can just imagine the boom in students interested in STEM if they could actively participate in science missions rather than learn about them as spectators. Now, beyond this, you could also think of a practical use for plug and play as a way to make your missions last longer. If we're able to replace an aging or failing component, your mission is no longer limited to the life of the weakest link component. If something starts to fail, you could fly up to it and swap it out for a brand new one and continue operating your vehicle just as you have, making especially the more expensive things, the national security satellites, giving them an opportunity to last longer and make your tax dollars go further. Now, this plug-and-play interface, making this not only a reality, but making it scalable in the way that we have with commercial electronics, we're really going to rely on flight software to bring us into that realm where this is achievable and scalable. So this then brings us to the next big step, which is in-space assembly. From the knowledge that we gain from doing refueling and doing on-orbit augmentation, upgrade type missions, this will really lay the foundation for us to then develop our technologies, our capabilities for in-orbit assembly, which would then allow us to do more sophisticated things, more sophisticated plumbing connections, more sophisticated electronic connections. It would allow us to do things like in-space welding. Spacecraft wouldn't have to be fully assembled when they launch. Now, it's going to sound kind of far-fetched, but you can imagine IKEA for space. It's something that's packaged for shipment, for launch, and assembled on site. And it sounds kind of silly, it sounds kind of far-fetched, but the idea, the benefits that are there are very real. Being able to rethink how we package things for launch means that we may be able to pull out efficiencies from our launch vehicle that aren't possible today without changing anything about the rocket. We're just changing how we get the satellites onto the rocket. And this then brings us to the next thing. And this is where, at least for me, it feels like we're really starting to get into the future. It feels like we're living in an episode of the Jetsons. This is in-space manufacturing, making things in space. So additive manufacturing, things like 3D printing, it's already spread in our commercial world. It's everywhere. My daughter actually has a 3D printed dragon toy that she got that I keep finding myself looking at because it's so cool how they did it. That they did multiple colors. The transitions are so smooth. They actually have articulatable joints that, because it's additive manufacturing, they were printed already connected. They weren't separate things that were then later assembled. So that what we're able to do with technology today feels like we're living in the future already. So as this technology continues to develop, I guarantee you it's going to find its use off the ground and in space. We already have this in space market already, but it's mostly limited to ground applications, things like rapid prototyping. But if we can manufacture things in space, things like new tools, new brackets, it's going to allow us to respond to needs much more quickly. I'm not sure if you guys are aware, but the time it takes to get something in space, from the time you identify a need, develop a solution, manufacture it, test it, get it on a rocket, get it in space, it's a year, maybe 2 years for even the simplest of parts. And that doesn't include the time to get it from wherever the rocket drops you off to the point of use. If we were able to actually print the solution in space, we could take our response time from years to weeks, allowing us to respond much more quickly to the needs of our customers. And this, with in-orbit assembly and in-orbit manufacturing right on the horizon, now is a really cool time to be in space. And again, we're going to rely on software to make these things a reality. So with all these capabilities, when you put them all together, when you have the rendezvous, the proximity operations, the ability to move propellant between vehicles, the high precision robotic operations, in-orbit assembly, in-orbit manufacturing, you get to a point where you can then support in-orbit recycling, the ability to move assets from one vehicle to another, utilizing your in-situ resources. Now, not only does it take a long time to get things into space, but launching is one of the most expensive and riskiest aspects of any space mission. If we could take that out of the picture and reuse or repurpose assets, whether they're raw materials or actual components, things that are already in space, if we could repurpose those, we can make space more accessible and more affordable. Now, all of this, all these technologies, if you put them all together, what it really gets us to is being able to respond to evolving needs after launch, putting what we need, where we need it, when we need it. And this is going to drive down the cost of our space missions, making our missions, the economy as a whole, more efficient, more agile, and more sustainable, which will allow more people, more groups to participate in our space economy. So as we move into this new paradigm for space missions, we're going to need to rethink how we think about space missions. And there's, I got a couple of examples here, but this is really just the tip of the iceberg, but I thought these were somewhat more pertinent to flight software. So one of the things that we need to rethink is how we allocate decision-making between on-orbit flight software and the ground operator. So traditional spacecraft, they tend to allocate the complex decision-making to the ground. And they do this for two main reasons. The first is that simpler is better for flight software. If you ask them to do more complex things, they need to navigate more logic paths, which means more testing, more complex validation. It also means it's more opportunity for an untested corner case or race condition as we start putting multiple processes together. In short, it's an opportunity to make the wrong decision if you ask them to do more complex things. So for this reason, we tend to rely more on the ground operators to make the complex decisions so we can keep flight software simple and make the qualification campaign more affordable. The second reason is space is big. Your nearest neighbor is kilometers away. You're usually not in immediate risk of collision. With the luxury of space, you get the luxury of time. With the luxury of time, you can go slow and steady and make the safe move, which typically means if you have a major anomaly, you go into a safe mode, which will interrupt certain activities. Maybe it'll slew to a different attitude. Then you wait for the ground operators. They get involved, they investigate, they come up with a recovery plan, and they get the asset back online. Now, there is a balance, because when you come offline and you get into a safe mode, you pull your payload off of doing what it's supposed to do. Maybe you lose revenue if you're a communications satellite, or you miss scientific opportunities if you're a science payload. So there is a balance where we do want the software to be able to do enough to keep your satellite operational through the simple stuff, but if it runs into a complex solution, we really do just rely on the ground to cover the more complex things, to keep software easier and to keep the test campaigns more affordable. Now, on the other hand, due to their nature, satellite servicing missions are going to require us to reallocate some of that responsibility back onto flight software. Now, what do I mean by their nature? In order to service something, we typically need to get very close to it. We need to do rendezvous and proximity operations with multiple vehicles involved. For MEV, that was 2 vehicles. For MRV, that might be 3 vehicles if we're installing a MEP. And when I say we get close, we get so close that a small thrust error or an unexpected slew could be hazardous and cause a collision between these vehicles. And the inopportune failure of any of the vehicles could put all 3 of them at risk. The luxury of time is no longer on our side, and the tolerance for making the wrong decision is drastically reduced. So because of this, we need flight software to make decisions that we can't wait for the ground operators to make. And this might not seem too daunting at first. I mean, this is a flight software workshop. This is what we do. We make flight software. But a couple things to keep in mind when we go through this. The definition of safe for a servicing mission is not the same as safe for a standard mission. There's a lot more parameters to consider. We need to contextualize your decision-making based on the operation. What's safe in one operation, one scenario, may not be safe in another. To give you an example, if you're far away from whatever you're servicing, if you're just starting the rendezvous process and you have an anomaly during a burn, one of the safest things you can do is just abort the burn and figure it out. But if you're meters away and that's actually your braking burn as you get close, stopping that burn is the last thing you want to do. So the same solution doesn't fit for all things. Doesn't mean safe in one is safe in another. Now, we're also going to have more computational demands for the flight software to navigate. As the complexity and the variety of these missions grows, we're going to ask flight software to do more. Flight software is going to have more stimuli to process, and they're going to have to do so with more complex algorithms, things like machine vision. Again, we're going to ask you guys to do more to keep the spacecraft safe. Robustness through simplicity is no longer an option, and simple is not always going to be better. The bottom line is we're going to need flight software to process more data, navigate more complex decision, logic paths, and make the correct decision quickly and reliably to keep everything safe. So another major thing that we need to rethink is how we plan and prepare for these space missions. I'm actually going to, so classical traditional space missions, they typically are designed for a well-defined set of objectives. You know what your mission is when you kick it off, you design it, you launch it, you operate it. The mission is defined early and consistent. Now, sometimes the mission is more well-defined if it's a geocom, for example. Your mission is to get to geo and point to a spot on Earth. It's pretty simple. If you're a science mission, maybe it's a little bit less defined. You got to follow the science a little bit. You know, maybe you get up there and you find that you use one sensor more than you thought you would. Maybe you're looking at asteroids and you find this one way more interesting than this one. So you're going to change a little bit, but what you're really doing is magnifying certain aspects of your mission and reducing others. You're not changing the overall structure of the mission. Now, of course, we're going to respond to circumstance. If you have an anomaly that reduces your capability or takes something offline entirely, maybe your mission gets shorter. Or maybe on the other end, you have a mission that's exceeding expectations and you extend the life well beyond its initial plan. I have a friend of mine, his mission, it was designed for 2 years and it just passed 6 and it's still going strong. So it does happen that these missions just keep going and going and going. But again, we're not really changing the structure of the mission. We're shortening it, we're extending it, but the ground team knows what to expect. They can plan for it, they can test like they plan to fly, and then fly like they tested. And along these lines, you also know what you're going to launch with. You know your consumables, you know your avionics, you know your payloads, if there's any hosted payloads. With the exception of missions where an astronaut comes in and lends a helping hand, there's no way right now, there's no capability to replenish your consumables, change your avionics, upgrade your payload capabilities. Now, software is one of the things that you can actually change after launch, but even that, it's typically limited to patches, small fixes. It's not entirely new rebuilds, it's not entirely new capabilities, typically. I have a story later on for that. Now, conversely, future space missions, they're going to evolve throughout their life. That's going to be the baseline. So let's start talking with the servicing vehicles, something like an MRV. It's designed to respond to the real-time needs of the client. If a client could tell us every anomaly that they're going to experience for the next 10 years, we could plan our MRV mission just like a traditional space mission. But that's not how anomalies work. They come up and they're going to be unexpected. We could test and plan for 100 different scenarios. It's going to be the 101st that we're called on to address. Now, that new scenario, it may require us to use our capabilities, our tools in brand new ways that we've never thought of before. Or it might be entirely new tools or new algorithms that need to be developed after launch. We really need to learn to adapt to these evolving situations, evolving needs that pop up throughout the mission. Basically, we're going to know how the mission starts and ends, and everything in the middle is going to be filled in as we go. This isn't limited just to the servicers. On the client side, if they're properly outfitted with the right interfaces, as we talked about before, they can also evolve throughout their mission life. MEV already is able to extend mission life well beyond their design, well beyond where their propellant runs out. We're also able, MEV1 relocated its client to a whole new spot on the geobelt, so it could service an entirely new geographical region that it was never intended to do. The operators had to adjust, and we had to find new ways to operate the spacecraft from how they've been doing it for 15 years. Refueling ports, we already kind of talked about this. If you have a refueling port, it opens up entirely new strategies for propellant management. That might mean launching with less propellant. Again, launch vehicles have a certain mass that they can lift to certain orbits. Maybe you just shift your allocation away from the propellant and launch more payload with the same mass. Then you just plan to refill when you get on orbit. Or maybe you plan more frequent maneuvers and just refill as you go, kind of like we do with a car. Or maybe you don't actually change anything about your mission profile. You launch the same way, you operate the same way, but now you can plan for a longer mission because the volume of your tank no longer defines the life of the mission. You're no longer, the last one is on-orbit augmentation. Again, we talked about this one, but being able to plug in new things throughout the life means that we open up the opportunity to respond to new opportunities, new threats, new market trends throughout the life of the mission. This might mean a new scientific instrument for science payloads, science missions. It might be a new radio or a new communication device. I mean, a lot of things were launched with RF technology right before optical became a reality. So I'm sure they would love to have optical capability to do crosslinks or downlinks. Could be new cameras for space domain awareness. This is a new thing that's coming up. We're not the only one that are doing these on-orbit rendezvous capabilities, and there's a lot of interest in knowing what else is out there, what capabilities they have, and who's approaching us. So being able to just add on a camera to existing assets would be very valuable. Again, just imagine the breadth of plug-and-play options available to your phone, available to satellites. We will no longer be limited to the paradigm of what you launch with is what you have available. Now, again, just like with the servicer, the customer, they're going to need to be able to respond to these evolving missions throughout their life. So you may be asking yourself, this is all cool, but what's the connection to flight software? So I'm going to leave you with 3 challenges that I think flight software needs to address in order to make these new capabilities, the future of space missions, into a reality. So the first is you're going to have to do more with what you have available. So what do I mean by do more? Well, as we increase mission complexity or the difficulty of specific operations, we're going to demand more from flight software. Process more data, make more complex decisions, respond quicker to keep things safe. Missions that include rendezvous and robotic operations, they rely heavily on machine vision and high-speed signal processing. Today, we're able to safely rendezvous with fairly large satellites that our machine vision can detect from long ranges. In the future, we're going to want to service smaller vehicles, so we're going to need better machine vision that can detect and track these small satellites, even with like the Earth in the background. Soon with MRV, we're going to be able to do some robotic operations, grab here, push there. But in the future for in-space assembly, we're going to need better signal processing for more fine motor skills to be able to do things like tighten bolts or plug in a connector remotely in the geobelt. Now, what do I mean by with what's available? I think someone yesterday mentioned space avionics are 10 to 15 years behind current terrestrial technology. Avionics that go to space don't advance very quickly. So we can't rely on having more computational resources. We need to be able to do it with what we have currently available. So what this really means is we need our code and our algorithm to continue to develop their efficiency to use what's available more efficiently and effectively. Now, I heard some strategies through the last couple of days of ways to prioritize make sure the high priority tasks have the resources that they need when they need it. Things like priority scaling or space-time partitioning to make sure we allocate the right resources to the right tasks. As far as I could tell, those were static definitions. We knew a priori what the high priority was. In servicing missions, we're going to need that to ebb and flow a little bit. The highest priority task in scenario A may be a medium priority task in scenario B, and we're going to be maximizing all of our resource utilization, so we need to be able to dynamically reallocate how we give out those resources. Now, I've seen cases where people knew underlying theory, they were the subject matter experts of something, but they really weren't software engineers, but they were asked to create a software product, whether it was a ground tool or an algorithm for space. And because they knew the theory, but they didn't know how to turn that into efficient code, the results were kind of what you would expect. They were able to get the right answer, but not in the most time or resource efficient manner. Now, when I was a grad student at Georgia Tech, I was in a high performance computing research lab where we really looked at ways to make algorithms more efficient using GPU and other techniques. This was early in the GPU processing times. So when I got into the industry and I saw these products being produced that were really inefficient, it was kind of a hobby of mine to take these inefficient code, tweak it a little bit, and come out with a product that still got the right answer, but an order of magnitude faster using much less computational resources. And we really need this. I had to kind of do that in the dark of night because none of my program managers wanted to pay for better. We need to kind of rethink this. We need to change the culture of that. We really need to support this idea that we need algorithms to be more efficient. We need them to be better. Just because an algorithm can get the right answer does not mean that it's fit for purpose. Now, along those lines, if there's any program managers in the audience, you're probably hearing things like new algorithms and more complexity, and you just start seeing the dollar signs pile up. So this is the second challenge for software. We need to find more sophisticated ways to develop, qualify, and maintain our software so that costs don't spiral out of control. Now, I'm going to break this into the three things I just mentioned. The first is developing. Now, again, I'm not a software engineer, so this is my suggestion, but I welcome all your brains to really think how we can do this more effectively. But one thing I think we can do is emphasize code modularity and portability for reuse. Now, on the previous slide, I talked about optimization, making things as optimal as possible. But there's a balance there. If you over-optimize and you make it so custom that you can no longer take code from one vehicle to another or one mission to another, you may have actually done yourself a disservice. If the code was good enough and it was portable, we need to recognize good enough is good enough. Being able to reuse code means we can leverage more abbreviated qualification, focusing really on just what's new. So reuse will make our qualification more efficient and more affordable. Another aspect is flight software spans many different disciplines. We got GNC, we got fault management, we got all kinds of different applications for flight software. And with this, different groups may develop their own coding styles, their own coding languages that, of course they're all going to work, but maybe you have to massage a little bit to get them to work together. If we can really establish, and I know we've established many times over, but if we can enforce common standards for coding that make different groups code more interoperable, more plug and play, being able to take the vision processing and plug it right into GNC and see how it all interplays, that's going to make our qualification much more streamlined, much more efficient. Now, on the other side, with big companies like mine, Northrop Grumman, you have GNC over here and you have GNC over there. They don't talk, they don't know what each other are working on, so they may be solving the same problem twice. They may be reinventing the wheel without even knowing it. So one way that we can maybe address this is having some kind of a centralized resource. I consider it like a library with librarians, if you will, that really pull together all of the qualified software products across the company, and it becomes a resource for new programs or to go to and say, hey, I need software that does X, Y, and Z. And they'll show you everything that's available, how it works, what it does, and you just leverage what's already available. You take what's already been qualified and plug it into your mission. Now, maybe there's inevitably going to be cases where there isn't a solution that you need. You go off and you develop that new thing, and once it's qualified, you bring it back to the library, you make it available for somebody else to leverage. Now, the second thing is how we test and qualify. And I've kind of gotten into this a little bit on the previous one, but servicing missions, there's an uncertainty in their mission. We know the start, we know the end, everything in the middle is undefined. So if we come up with a test campaign that covers 100 different scenarios, we're going to run into the 101st. If we've got 1,000 different scenarios, we're going to encounter the 1,001st. It's no longer practical or financially feasible to cover every possible scenario that a servicing mission is going to encounter. So instead, it may be more efficient and effective in the long run to focus on core capabilities, the building blocks of a mission. Make sure those work exactly as intended and make them ready to be used. And then as a mission becomes well-defined, you know which client you're servicing, what the problem you're addressing is, where they are when you're doing it. You know the who, what, when, where, why. You take those building blocks that you need, you assemble it in that specific mission, and you qualify it for that mission. You're no longer testing out hundreds and hundreds of scenarios. You're now doing the specific ones that you're actually going to encounter. And over time, you're going to build up a library of missions that you have tested and qualified. And over time, there will be a return on investment because you'll find qual by similarity because you've done this mission before, or you've seen this client before, so you can leverage the qualification and become more efficient over time. Now, finally, maintaining software. When we take something from a central archive and plug it into our mission, the likelihood that it's going to be exactly plug and play is pretty low. We're going to have to tweak things here and there. We're going to have to make, maybe it's your spacecraft ID is the only thing you have to change, but you change something about the code. We need a way to quickly validate those small changes, make sure that we haven't broken anything, make sure our core capabilities are still there. The MathWorks demonstration yesterday kind of hit on this, a set of quick checks that tell you that your code is still good, it still does what you expect it to do, rather than generate mountains of data that then someone has to go parse through and post-process and take the time to really think about. Being able to invest in these kinds of tools up front that make the maintenance of your code easier is going to pay dividends and make you more effective and more efficient in the long run. Basically, reducing the cost to develop and qualify software through reuse and focusing on testing just enough is going to be essential to this concept of figuring it out as we go and making it affordable to support that infrastructure. So finally, we're going to need the infrastructure to support these mission profiles that evolve throughout their life. We're going to need to be able to test things on the ground well after the assets have launched. Things like uploading a new software, it's no longer going to be the exception. It's going to be the norm. We're going to need to do it. So this is going to require some kind of ground twin. We've heard some about digital twins. Maybe it's a physical twin. Maybe it's something in the middle. Maybe it's not twins, maybe it's triplets, quadruplets. You have multiple different test beds. But this is going to require the forethought early in your program to make sure that these ground twins are developed, validated, tested alongside with the flight vehicle so that when we launch the flight into space, we know what's left on the ground accurately resembles the flight asset with the proper level of fidelity. To that end, we also need to maintain the ground just like we maintain the flight. If we upload a new software patch, it needs to be applied to the ground twin. If we add new hardware capabilities, new plug-and-play payloads, the ground twin needs to reflect that so that as we go through the mission, what you have on the ground accurately represents what you have on orbit. Now, with a well-qualified, well-maintained ground twin, we can use it as a test bed for new algorithms, for new operations, especially when you do robotics. You're going to want to practice the reach and see if you're not actually damaging something unintentionally. You can use it to train new operators. As these missions go for many, many years, you're no longer going to be in a quiescent state where you can just plug some fresh out in and say, make sure the lights are green. We're going to be doing active control for the life of these missions. Now, on the flight system side, we need to make sure that they're designed to accommodate these large changes. Being able to is not the same as being designed to. So I mentioned earlier about software is usually small patches that we upload, but not always the case. So I worked on a program where we actually launched without software being fully developed because we were told, hey, you can update software after you launch, no problem. So we did that. We made sure the hardware was working. We launched. And when the software patch came through, we realized, well, this is way bigger than we thought it was going to be. Our system wasn't designed for something this big. So what we ended up having to do is figure out how to make it work. What we did is we took this big software patch, chopped up into little bite-sized packets, no pun intended, uploaded over really slow RF links. I mean, the uplink was not designed for bandwidth. It was designed for one-off commands. Collect it in something that, the memory space that wasn't actually where it was intended to go. Move it through the system through backdoor channels, compile it where it needed to be, reapply it, and then recompile the patch, apply it. It was tedious. It was extremely frustrating because the system wasn't designed for such big patches, it had no safeguards. If you transmitted 99% of your packet, that last 1% was a little bit ratty because you had a cloud cover or something come through, you threw away the whole packet and started over. I got to emphasize, the system was able to be updated, but it wasn't designed to be. And we lived through probably a month of trying to update it because it just was so frustratingly difficult to make it work. Work with your program early in the program to make sure that they know that in order to support these updates, you need to design in certain features that traditional spacecraft don't typically have. Now, as we make the system easier to update, we have to keep in mind, we don't want to open up the door for new problems. We don't want a bad actor to upload rogue software and then get that applied onto your spacecraft. We don't want ratty comms to then corrupt a patch that, you know, we don't catch and we apply a corrupted patch. So don't sacrifice safety and integrity to make it easier to update. I think we all understand that pretty well. But as we move into this new paradigm of expecting these missions to evolve and require major updates throughout their life, we need the forethought and planning. We need to ensure that the ground infrastructure is there, it's validated, and it represents the flight model. We need to make sure that the procedures are in place to maintain the ground swing so that it continues to represent the flight model. And we need to make sure that the flight model is designed to accommodate these large updates throughout their life. And these must be primary mission objectives. These are not secondary afterthoughts that, oh yeah, it would be nice if we plug this in. So to close, I'm going to bring us back to this roadmap. I'm going to reemphasize this is a really exciting time to be in space. We have a whole host of new capabilities coming online, and what that means for space missions and our space economy as a whole, it's still to be seen exactly the extent of the impact. And it's really exciting to be on the horizon of all of these new capabilities. And we're excited to keep pressing it and seeing as we go through these capabilities on the bottom, what that does to our industry. And of course, software is going to play a pivotal role in making all of these capabilities actually achievable and practical, and make it something that our space missions can leverage. So I know we're about halfway through this workshop, but as we go through, please keep an eye out for ways to make your software more computationally efficient and robust, ways to make it more portable and more testable, and learn more about digital twins or ground twins, because I believe these are the keys to success as we navigate this evolving landscape of space missions. Thank you for your time.
Okay, so we have some questions. Online question, what sensor suite is used for the approach and docking for MRV and MEPS?
We have actually, so we have a large sensor suite. We have visible cameras, IR cameras, LiDAR. We have wide field of view, narrow field of view. We have monocular vision algorithms, and we have binocular vision algorithms. We kind of covered the suite of every possible thing that we could put out there to make sure that we're double, triple, quadruple redundant.
And kind of a follow-up, what kind of propellants do you support? Are you tackling cryoprop?
What was the first part of that?
What kind of propellants do you support?
Oh, so we have electric propulsion with xenon and chemical propulsion with hydrazine. We are not looking into anything that's too far out there with propellant. We're getting plenty of performance from what's already commercially available with EP.
Hi. My question is, how agile development practices can help achieve such a vision, and how can they mix up with, safety critical requirements and more traditional development process?
So overall, we see benefits in Agile, especially as we create new things. Unfortunately, our company's culture hasn't shifted enough to the Agile way of thinking. And I'm sure many of you have seen, if you halfway implement Agile, it's not Agile. And we've kind of been handcuffed by trying to leverage as much old stuff as we can, and the old way of thinking was not Agile. So there's a lot of potential out there, we just haven't been able to realize it.
Can you talk more about when you're doing these servicing missions, how much the ground is in the loop? Are there autonomous decisions being made kind of as you're approaching the vehicle, by the vehicle, or, you know, is it kind of execute something coming from the ground, kind of wait, do the next thing from the ground, and what that latency looks like and what you see kind of in the future?
So I'll cover it a little bit, but I put my contact here in the QR, so there's some things I can get into more detail offline. We basically rely on on-orbit decision-making to keep the vehicle safe, not for mission success. So sometimes, to the frustration of the ground, the vehicle will say, this isn't safe, I'm getting out of here. We prefer safety over everything else. As I mentioned, GEO is where a lot of high-value assets are. And if you saw the movie Gravity, if you create a little bit of a debris cloud, it's going to go around, and it's going to grow, and it's going to get worse and worse and worse. So the last thing we want to do is cause any damage, cause any debris to shake loose. So safety is where our autonomy comes in.
So can you speak of the physics of on-orbit refueling? I'm curious how the vehicle will settle its fuel in the tank. Ullage thrusters? I don't know if that's...
So that sounds like a very specific, detailed question. I'd have to take that one offline. I'm pretty sure that the refueling group is a tangent group to mine. So I know they've published papers on on-orbit refueling. They've made their interface open, so anybody can buy the PRM and plug it into their vehicle. And I believe with that, it comes with a user's guide for how your vehicle would be refueled. So if there's specific questions on how exactly it works, please reach out to me. I'll make sure to get you in contact with the team that can answer all of your questions and more that you probably want to know.
No? Okay.
So your mission holds significant value. Could it expose the satellite system to the risk of side channel attacks and broaden your attack surface? If so, how would these risks be mitigated?
So I'm not sure I fully understand the question, but in general, satellite servicing does open up a whole new channel for bad actors, whether they're state-sponsored bad actors that are going to come and, you know, mess with our assets, or if somebody were to get into our system, they might actually be able to do things that we don't want with our own system. So we are implementing a number of safeguards on that. We've been working with DoD and others to ensure that our spacecraft meets all of their standards for cybersecurity. So we're controlling our attack surface there. But that does nothing to say what other countries are able to do with similar technologies. I think China demonstrated right around the same time as MEV the ability to go up, grab another satellite, and bring it well above the GEO belt, take it so far out of orbit that it would never get back. So other countries have these capabilities, and we need our own systems to be aware of that and protect against it.
Okay, so this will be the last question. Between life extension and refueling, which model do you think will become more dominant by the end of the 2030s? Is there a refueling port or standard you endorse?
So I think that life extension is more backwards looking in servicing the unprepared customers, the ones that they're already up there, they've never planned to be serviced. That's where life extension really helps. If you're able to be refueled, you no longer have to think of this extra mass plugging into your vehicle, and there's extra complications that come along with satellite servicing. So being able to just refuel and go would probably be the preferred one moving forward. I think there was a second part of the question.
Well, I think you answered it.
Is there a refueling port? Well, I'm sorry. Oh, no, there's not. It is different. Is there a refueling port or standard you endorse?
There is now a passive side. There's not an active side standard. So the passive side is, like I said, that's what you'll put on your vehicle. You don't have to do anything. It's there, and something can plug into it and flow propellant. The active side is the one that actually manages the flow of propellant. That standard is still coming out, but the refueling, the vehicle that gets refueled, that standard is out, it is published, and it's available to start being put on. We're actually putting that on to MRV, so MRV will be refuelable as a measure of our confidence in our refueling capabilities.
Thank you, Josh. Appreciate it.
Thank you very much.